All right, IB AASL1. Today we're starting a new learning target and we're going to talk about the reciprocal function, which is the British IB way of saying rational functions. So you might have seen these in other classes with this word rational functions. Rational functions always have an x in the denominator. So that's the way you can tell if something is a rational function. Before we get to rational functions, we got to talk about reciprocals in general because they come up a lot with this. A reciprocal of a number is just 1 divided by that number. That's one way to get to it, but I'm going to show you guys kind of a quicker way to do it. First up, these examples, we're going to find the reciprocal of each of these numbers. Now, this fraction is not in the right form to be able to find the reciprocal. So to be able to find the reciprocal, you have to turn it into a mixed fraction, or whatever you call that, where it's just a number divided by a number. So if it's been a while since you've done this, 4.5, you take the 2 and multiply it with the 4, which you get 8, and then you add the 1 left over and divide by 2, so this is 9/2. Now, I didn't find the reciprocal. All I did was just turn it into a mixed number, 9/2. This definition up here said it's 1 divided by that number. So if we go with that definition, the reciprocal is 1 over 9/2. But then, remember before when I've showed you guys how to divide by a fraction, you keep the top number, which is 1, and then you multiply by the bottom number upside down. So here, the reciprocal is just 2/9. Now, looking at 9/2 and looking at 2/9, we can clearly see that it just turns upside down. So if it starts out as number over number, you can just turn it upside down and then it's fine. The next example, 7m, you can think of this as 7m over 1 and then just turn it upside down. So it's 1 over 7m. Both parts need to go into the denominator, not just the 7. The last one, yes, you can turn it upside down, or you could do the 1 divided by x plus 1 over x minus 5, and then that's the same as keeping the top and then multiplying by the bottom upside down, so you get x minus 5 over x plus 1. But really, it just flips upside down. X plus 5 over x plus 1. Now I would like you guys to try this. You try. Find the reciprocal of 18 2/5. You guys get 590 seconds? Great. Now that we know what reciprocals are, the reciprocal function is basically like the reciprocal of x. So the reciprocal of x would be 1 over x, or in this case, we're going to do k over x, because you can have any number on top that's not an x. Or, well, any number except for 0. K needs to be a non-zero constant. And that makes it a reciprocal function. Please notice that x is in the denominator. That's what makes this a rational function or a reciprocal function. Now, we're going to talk about some qualities of the parent function of a rational function. Let's start with domain and range. Yes, we could graph this on a calculator and then analyze the domain and range visually. But I want us to think about just like what types of numbers can go in here. So if you put negative numbers in there, you'll get like negative fractions. If you put positive numbers in there, you'll get positive fractions. If you put fractions into this spot, you will actually get bigger numbers. Like 1 over 1/2 is 2 when you flip and multiply. So you can get positives out of this, you can get negatives out of this. Really, the only thing you can't get out of this is 0. Because if you think the only number, I'm thinking outputs. The only thing you can't put into this is 0. So the domain is going to be negative infinity all the way up to 0, but not including, and then unionized with 0 all the way to positive infinity. This is kind of an awkward way of saying this. I've seen other curriculums where they just say that x is an element of real numbers, but x cannot equal 0. That's maybe a more simple way to say that. Same thing with the range. I realized I was talking about it earlier, but if you think about all the different numbers that can come out of there, like if you put negatives in, you get negative fractions. If you put positive, you get positive fractions. If you put fractions in, you get whole numbers. If you put negative fractions in, you get negative whole numbers or bigger numbers. But you still can't get a 0 out of it because there's no solution to this. 1 divided by x is equal to 0. There's nothing that could, if you try to solve for x, like it just doesn't work. You're going to end up dividing by 0. So the range is actually the same thing, that it's all negative numbers up to 0, but then not including it, and then 0 up to positive infinity. Another way to say this is that it's all real numbers, but y cannot be equal to 0. Sometimes they put curly brackets around that. Terrible curly brackets. Oh, I'm getting better. Here, we'll just fix that. Now, what does it look like? I call rational functions the cobwebs. So this is jolly speak because no other math teachers use these terms, but it really they remind me of cobwebs in the corners of windows. This cobweb up here drapes in the top right corner, and then the cobweb on the left drapes in the bottom left corner. So this is what the graph of 1 over x looks like. It makes sense because if you think about like putting in larger and larger x values, you're just going to get a smaller and smaller fraction. Like if you make x 100, then your output is 1 over 100. So you actually get this asymptote relationship where the further out you go, the smaller the number is going to be. So there's a horizontal asymptote. Remember, horizontal lines are the equation y equals something, so this is y equals 0. Now, you can see the horizontal asymptote happen on both sides, like as you go out to negative infinity. So as you go out this way, like as x's get more and more negative, you get smaller and smaller negative fractions. That makes sense that it's in the negative zone here, because if you put in a negative, you get out a negative. So as you get more and more negative, the numbers get smaller and smaller negatives. Now, the reason that this heads up to positive infinity and negative infinity as you get really close to the x-axis, well, there's two reasons. Because you can't divide by 0. That's the reason that there's a vertical asymptote here. So every rational graph has two asymptotes. It has a vertical and a horizontal asymptote. And this one is at x is equal to 0. Now, if you think about why it freaks out as you get closer and closer to 0, if you think about taking, like, if this is 1 right here, x is equal to 1. So you plug in a 1, you get out a 1. Pretend that's a 1 right there. I really should have made these cobwebs touch right here. My bad. Well, I guess I can fix that by just saying, like, oh no, what did I do? By saying, like, this spot right here is 1, not that. So if this is 1, then you get a 1 out of it. So this is the point 1, 1. Now, if you take numbers that are smaller and smaller, like a 1/2, if you put a 1/2 into the function here, you get 1 divided by 1/2, which is 2. So that's why at 1/2, it'll go up to 2. Pretend that's 2. Then think about putting in like a really small fraction, like a 1 over 9 or something like that. If you put a 1 over 9 into the function, you get 1 divided by 1/9, which is 9. So the closer I get to the x or to the y-axis this way, the bigger those outputs are going to be. That's why it goes all the way up to positive infinity right here. Same thing when you approach from the left-hand side. Like as I get closer and closer and closer this way, those numbers are going to get bigger and bigger and bigger. Bigger, that's a word. And more negative because they're negative numbers. So it approaches negative infinity from the left. So it's a vertical asymptote. Well, there's two. There's a horizontal asymptote and a vertical asymptote. This happens with every rational function, is you have a pair of asymptotes. One on the vertical, one on the horizontal. Now, we're going to sketch the graph of y equals 12 over x, and we're going to label at least 2 points. Label all asymptotes. Eventually, you guys will get to the point where you can look at this and be like, oh yeah, it's like a cobwebs that's been stretched a certain way because all our transformations are still valid, but I'm going to approach it from a table perspective. So if you put y is equal to, or I should say f of x, 12 over something, and we're going to put different somethings in there. If you put a negative 6 in here, 12 divided by negative 6 is negative 2. So that means if I go out 1, 2, 3, 4, 5, 6, this point, negative 6, negative 2 is on the graph. Then if I put a negative 2 in there, 12 divided by negative 2 is negative 6. So if I go over to negative 2, 1, 2, 3, 4, 5, 6. Then if I put a negative 1 in there, you'll get a negative 12. So that means at negative 1, it's going to go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's going to be like way down here. So you can see that it's building sort of a cobweb on this side. That it looks something like this. Then if you put a negative 1/2 in there, once again, if you put a negative 1/2 into that, you have to flip and multiply. So if we do 12 divided by negative 1/2, this is the same thing as 12 times negative 2 over 1, which equals negative 24. So if I go to the 1/2 tick mark, that means I would have to go 24 spaces down. So it's going to get bigger and bigger and bigger the closer you get to the y-axis. If I put a 0, so that's negative 24. If I put a 0 in there, you can never ever divide by 0, so this is undefined. So I don't know how you want it. Here, I'll just put one. I'll just put a no. So that doesn't work. That's the reason that there's an asymptote at the y-axis. You can't feed 0 into that. Then if you put a 1 into that, 12 divided by 1 is 12. You put a 2 in that, 12 divided by 2 is 6. Put a 3 into that, you get 4. So then we go 1, 1, so 1, 1, 2, 3, 4, 5, 6. That's on. And then 2 is going to, oh, sorry, 1 was supposed to be at 12. My bad. So 1, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12. So that's way up here. Then 2 is at 6. Oh, that's 5. My bad. Going too fast. That's 6. And then at 3, we get to 4. So you can start to see, you know, if I were to plug in bigger and bigger numbers, they would get, the output would get smaller and smaller and smaller. So we would get something like this. So there's lots of points we can put on this graph here. I'm going to say that this is 2, 6, and this is negative 2, negative 6. So there, I labeled 2 points. Also, the asymptotes. There is a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. So we'll say vert asymp is x is equal to 0, and the horizontal asymp is y is equal to 0. Now, the parent function of the cobwebs can still be transformed the same way we've been transforming lots of other functions. So, if I think about this graph right here, negative 1 over x. Think of that as negative 1 times 1 over x. So you're multiplying by a negative 1 on the outside, which reflects the cobwebs over the x-axis. So rather than the cobwebs being here and here, which is where the parent function is, they're actually going to switch and be here and here. Sorry, I'll try to make those a little more uniform. Try to make them actually go through negative 1. There we go. So they look like that. I was trying to make them go through these points. These are like the anchor points of like over 1, down 1, left 1, up 1. Now, this next problem, negative 3 over x, is, you need to think of it like negative 3 times 1 over x. So it's a vertical reflection because of the negative, but it also gets stretched by a factor of 3. So normally these points would be on after the negative reflection, but then those are going to get tripled. So rather than being tripled in a vertical fashion, excuse me. So rather than negative 1, positive 1, it'll be negative 1, positive 3, and then positive 1, positive 3. And there will be like the flip of that too, where you could go negative 3, positive 1, positive 3, negative 1. So our cobwebs are going to look something like this. Now, the difference between these two pictures is, notice the distance between these two anchor points here is a little bit shorter, and here it has been stretched out. That's because the entire graph has been stretched vertically away from the x-axis. The last one, you need to think of this as being inside the function. So that means that the entire graph got shifted 1 to the right. So instead of the vertical asymptote being at the y-axis, it is now going to be right here at x is equal to 1. But then it's just your regular cobwebs that they come down, they touch 1 away from that center point, and then they go this way, touch through that point, and they look like this. So notice they are in different corners, opposite corners, than the previous two because they have not been vertically reflected. Your turn. Without using any sort of calculator or Desmos, please sketch both of these. All right, you guys, there's what your sketches should look like. Please ask me questions in class if you need some help with homework problems.